Hello, welcome. My name is Melissa Bowman, and this is my presentation for my master's research project at CUNY University. And this is on image classification accuracy with physics-informed invariance to reduce the MNIST data. So the main research question of this project is, can physics-informed machine learning improve accuracy of small sets of image classifiers? And what I mean by small data here is images, image classifiers that are less than 10,000 images in a data set. What I mean by high accuracy here is kind of your low variance, low bias, kind of that very classic image of the bullseye and all of your arrows hitting the bullseye, which this image was created by Imagen, and you'll see a couple of those generated Google Imagens around this presentation. But the real crux of the research question is physics in predictive models. Why do you want to put physics in predictive models? How do you want to do that? And what implication does it have for future AI? And we'll get into those. So why should we consider physics in machine learning? Physics at its core is the understanding of our world through physical laws, but that we then use predictions. And machine learning is used to make predictions, so it makes sense to combine the two. Machine learning models, though, don't commonly utilize physics. It's gaining popularity, but most models are just based on massive volumes of data. And the reason for this is that most predictive models, usually deep neural nets, are good predictors without physics if you have enough data, because it's learning the physics that's going along. So why then? Okay, if these deep neural networks can learn the physics on its own and implement it and make predictions, why do we care to put it there? There's a couple reasons why. Some models have reached their limitations with it. Consider maybe even an image classifier. Again, here's Imagen. I told the prompt was to make a W with your fingers in two hands, right? But you can see that it kind of starts blending figure. If we implemented physics into that, right, we would know that physically I can't meld into my own hand. Yeah, so if you feed deep neural networks without reinforcement learning of those physics, you start getting AI hallucinations, which is kind of like this melding of this image and this backwards hand. And in the future, we could optimize that. Physics to machine learning could also help future physics in that it can help start imagining physics that we never thought existed before, or help develop new physics. So not only can physics help with predictive models, but predictive models can help with that physics in the future. And then also we have the challenge of the black box problem. Your black box problem is about not being able to understand how these models are creating these predictions. When models don't, we don't understand how models are being predictive. We can't fix unwanted outcomes. We can't explain these systems, we can't be transparent with them, and then we don't know if they're introducing different biases. So definitely the reasons as to why, and even the future of why adding physics to machine learning predictive models is important. So how to implement the physics in learning models? So here is Professor Stephen Burton, University of Washington. And about a year ago, he posted these very comprehensive video series about physics-informed machine learning. I highly recommend watching them. I have the link here at the bottom. And here's a snapshot of that video and the link. And the reason why I took that, it's because here's him going over the 5 stages of building machine learning. And he is creating the argument that you can embed physics in each step in the building a machine learning model process. And in this experiment specifically, I went to curating of data. I didn't go to these are like more higher level design and architecture, crafting a loss function and employing an optimization. Even these two, this DMD and the Sydney models are actually PhD level experimentations. So curating data was more simplified for a semester class. So I'll be embedding physics into the data beforehand, like feature extractions. And for my experiment, I used the MNIST dataset, which is a set of hand-drawn digits from 0 to 9. There are 60,000 images in the training set and 10,000 of those images in the testing set. I use this because it's a very standardized, well-known data set that is available and small enough to work on localized computers. What I did with that MNIST data set was I reduced the data set by 5% and 1%. I chose these because they looked like accuracies that had some amount of area to improve on. When I did a cross-validation comparison with a convolutional neural network, the convolutional neural network I used for this is a very simple 2 convolution layer, 2 pooling activation function, very, very simple convolutional neural network. Cut it down to a 5% and 1%, which makes it 3,600 images respectively. So once I reduced the data set, I needed to figure out the right physics for a digital image. A lot easier said than done, because you have to understand the physics behind a digital image. This physics is static, it's not dynamic. They're 2-dimensional, they're matricized. So trying to figure out what physics can be done to this digital space. And the research I came up was in invariance. And what is invariance? And this is a simple illustration of what invariance is. Invariance is the property of remaining unchanged regardless of changes in the condition of measurements. So meaning like, if I have a rectangle and I rotate it, the area of these are the same regardless of where they are in that space. Theory was that if I took something like these digits, like a 3, and rotated it, it would still be the same 3. Maybe it would capture a rotation that someone was writing more diagonally or in a rotation. And I did rotation, and I didn't do, because there's other ones, there's scale and translational, which is just moving this or, scaling it down. Didn't do that because the MNIST data set was already, it has a specific scale normalized, is centered in the data set. So the only thing that it doesn't do is rotate, so I thought rotating would be simpler. There's also, wanted to put ranges in here because I was afraid that some of these digits would actually be more partially invariant to rotation. As you can see, like a 6 or a 9, if you rotate a 6 or a 9, and if you put that in the prediction as, this 6, and you rotate it and you still say this is 6, it could mistake 9s for 6s. So I put ranges of these rotations, and the ranges being, I put negative 45 degrees to 45 degrees in 5-degree increments, and then did that with 90 to 90 degrees, same degrees of increments, negative 180 to 180 degrees every 5. And I added those all to the MNIST data. Now I got these bigger data sets with rotational invariance. And the results were the following. Yeah, these were not results that I was very happy with. If you look at their original 5% test accuracy, you get like a 96%. And then you look at the like 45 to negative 45 to 45 range rotations, you get less than. So that's not improving it. Then you get this 180, negative 180 to 180 degree in the 5, and it gets slightly, but it's even the 1%, it's nothing to write home to. And I was like, okay, maybe test accuracy is one part of it, and then could this still be a good training model for test data that for other images in the MNIST dataset that it hasn't seen? These models were not good fits. As you can kind of see in the 5% learning curve loss comparison, you see that it's a good fit because the validation loss, which comes from the test data, is very close to this training loss. Where you start looking at the rotations, these are overfitted like crazy. And it's the same for the 1%, even much worse. So these weren't good models for improving accuracy or predicting future outcomes. And this really surprised me. Most of the research I was doing really pointed to invariance of some kind, hoping that I would see something improve the information. It kind of discouraged me to think that maybe did I have to go into more advanced methods of that, that Steve Burton talked about, of like designing, crafting, and optimizing in this invariance. But then I came across this one paper that mentioned elastic deformation. This paper is by Simard, Steinkertz, and Platt, and this goes over elastic deformation with convolutional neural networks. So, what is elastic deformation? Elastic deformation is still an invariance. There is rotational, translational methods going on here. On a fundamental scale, elastic deformation is just the temporary shape change that can self-reverse after a force is removed. Me bending something, as I bend it and I let it go, it goes back to its shape. That's elastic deformation. This specifically how it works in image classification is that creating this displacement field that takes every pixel in the image, and each of these pixels are moved by a magnitude and a direction that then is run through a Gaussian filter that kind of smooths over these edges so that it creates a more continuous shape, and which that Gaussian filter is has a constant that is a sigma, and then there's this intensity of this warping, which is another constant, which is this alpha, and you get from like an 8 to a formed image, and then this is a warp image of the displacement of the vectors, and you can see kind of the pixel and where it's being moved to in the space. Instead of moving the whole image, you move the pixels. I took this information and I applied 2 different elastic deformations with those 2 scalar values that I mentioned. The sigmas I kept the same out of 4, and then I changed the alphas to change the warping just to a 1.4 and a 1.7. And I did 1 elastic deformation and added that to the reduced MNIST data form, doubled it, and then I did it again, and then it tripled that reduction. So, like, for example, the 5% went from 3,000 images to 6,000 to 9. So that was significantly less than the rotational results of the elastic deformation. So it improved it. You see in the original 5%, you see this 96% test accuracy. Then you see the first elastic deformation you still see a 96%, but it increases slightly. And then you see 2 elastic deformations added to that reduction, that 5% reduced MNIST data set. And you see a 96, almost a 98% improvement. And then if you look at the 1%, it was 88%, and it jumps up to 92, almost to 94%. So it looks good so far with the test set accuracy when compared to data sets that the training set has not seen before. And if you look at the learning curves, you see, although not perfect, these are still quite overfitted. Again, comparing it to the original, but much better than the rotational invariance from what we saw. And even at the 1%, again, slightly just slightly overfitting, and it's also pretty good, but it's still overfit, but I think can be improved. So from the data and from the experiment, physics-informed machine learning can improve accuracy in small data sets. But it's a matter of choosing the correct physics and physics type. So it takes effort to figure out the correct physics needed. So here, this kind of proves that physics-informed machine learning can improve accuracy in small data sets, but need proper research to choose the correct physics. The results of this experiment proves that even if you implement physics into predictive models through augmenting the data, you can improve its accuracy. And this further proves that applying physics principles, there are valid improvements to machine learning models. Although my experiment is one of them, there are present-day examples of that. If you haven't seen VO2 from Google, it's a video classifier. The video quality of these are very advanced compared to most of its competitors. And from what I've been hearing from the reporting, it has to do with implementing physics into these video creators, which I'm curious to see if that is the case. I've been trying to get my hands on it. I'm on the wait list. If you want, you can look up alpha geometry, where it actually uses physics as Euclidean geometry to create completely synthetic data to compete in mathematical Olympiads that are usually notable milestones for AI machine learning to use to indicate if they could solve problems on the level of humans. And then if you really want to see what physics can do with machine learning, look no further than neural networks. Neural networks are based off of the field of electromagnetics that this year, 2024, won a Nobel Prize. So the point that I'm trying to make is that in the data science space, we all need to start really marrying the idea that physics needs to not only be here, but is an important and almost intrinsic part of the machine learning process. So that's my presentation of my project. I want to thank you for listening, and I hope you enjoyed my presentation. Thank you so much.